convenio del Laboratorio Internacional Asociado. Quisiera presentar primero a nuestro director, el doctor Miguel Alcubierre.
Muchas gracias, Pili. Buenos días. Bueno, para mí es un honor y me da mucho gusto poder presentar a nuestros dos invitados el día de hoy. Estas charlas que van a ver el día de hoy son parte de un convenio de colaboración, realmente un laboratorio internacional asociado a la CNRS, que es el equivalente más o menos del CONACYT en Francia, es la agencia de financiamiento científico en Francia. Y entonces ahorita hay un convenio, un laboratorio asociado que implica que hay intercambio de estudiantes y de profesores entre laboratorios en Francia, en particular en Toulouse, y diferentes laboratorios aquí en la UNAM. Entonces, esta visita es parte de la continuación de esta colaboración y me da mucho gusto tenerlos aquí. Y bueno, pues sin más, yo creo que sería importante pues ya iniciar con la charla. No van a ser dos charlas, pero la que se sabe los títulos explica.
Bien. Quisiera presentar muy brevemente al profesor Asedin Boussexou. Él es el director. Sí, bueno, muchas gracias, bienvenidos. Que venga para acá. ¿Sí? Bien, quiero presentar al profesor Asedin Boussexou. Él es el director del Laboratorio de Química de Coordinación en Toulouse, Francia. Él es miembro de la Academia Francesa de Ciencias, de la Academia Europea de Ciencias, de la Academia Europea de Ciencias y Artes. Actualmente es el jefe del grupo de materiales moleculares biestables desde el 2013. Es director de este instituto y bueno, entre sus múltiples, tardaría mucho tiempo, entre sus múltiples colaboraciones puedo destacar que él cuenta a la fecha con 250 artículos, 6 por invitación, 6 reviews por invitación, también 7 ediciones de artículos, además 4 capítulos de libros, 11 patentes, 8.018 citas aproximadamente, tiene un factor H48 y bueno, él ha tenido una serie de contribuciones de un impacto muy original de innovación en el área de materiales. Presentado más de 74 pláticas invitadas, 26 seminarios, 244 presentaciones orales, por mencionar simplemente parte de sus contribuciones. Él va a presentar la primera plática. Y bueno, quisiera de una vez presentar al doctor Leonel Salmón. Él también forma parte del grupo del doctor Boussexou, del Laboratorio de Materiales Biestables, y él pertenece también al Laboratorio de Química de Coordinación. Básicamente podemos destacar del doctor Salmón, él se dedica básicamente en la parte de desarrollo de materiales biestables, la parte química. Tiene 149 publicaciones, 3.668 citas, un factor H de 34, 3 capítulos de libros, 6 patentes, bueno, además de una serie de contribuciones, tanto la formación de recursos humanos como en la parte de contribuciones en el área de materiales biestables. Entonces, bueno, vamos a iniciar con las pláticas y no sé si quisiéramos darle la bienvenida. Sí. Por favor.
Bueno, antes de iniciar también quiero darle la bienvenida, no sé si ya todos lo hubieran entrado, al profesor Albert Fert, premio Nobel. Bienvenido, profesor. Bien, pues ahora sí empezamos.
Bien, pues sin más preámbulo, iniciamos con la plática del doctor Boussexou. Bienvenidos.
C'est bien, c'est bien. So, thank you very much for the introduction. First of all, I would like to say that I'm very happy to be here to make exchanges and collaborations. We have already many connections with Mexico, with Mexican students and groups. We have Edna here, okay, who did her PhD thesis in the group, and now she is dealing with her group. So in Toulouse, we have what we call Laboratoire de Chimie de Coordination, which means that we are making molecular systems by coordination chemistry, and then we are CNRS laboratory. So then, to explain quickly, our lab. It's something like 300 members, and then we have 15 teams. So then our organization is based on making molecules, making molecules by coordination chemistry, and then the differences between groups is the applications. So then we have groups around in the interface between chemistry and catalysis, groups who are working between chemistry and materials, and groups between chemistry and health. So then our group in Toulouse, we are dealing with switchable molecular materials. So then what we want to do in the group is to focus on systems in which we make in the laboratory, where you have two spin states, and the two spin states are close in energy. They are so close in energy that you can switch from one state to the other one by temperature, light, or pressure. So then you have switchable materials. Why we want to make switchable materials? You know, now we are in the situation where we need smart materials. So then these materials can be called as smart materials. Why? Because you can address them by temperature, pressure, or magnetic field. And then because their properties are changing from one state to the other one. For example, you can have a color change between yellow to red by applying temperatures. So then these materials can be addressable, okay? So then in the group, we want to make these molecules because we want to make the protocol, the synthetic protocol, in order to have molecules where you have two spin states which are quite close, okay? So then this is the synthetic part of the group here. And then we want also to make thin films. So then we want to fix this molecule into surfaces. And the question for chemistry is that you want to fix the molecule on the surface, and then you want to maintain their properties. Because you know, when you try to fix a molecule in surface, you have many interactions with the surface. When you have a balanced situation where you have a tiny equilibrium between two spin states, which is quite fragile, generally you lose the property of the bulk. And then the question is to make thin films. And then we try to do physics, solid state physics, in order to study the electronic properties, the photonic properties, and even the mechanical properties. So then what we want to do is, concerning the photonic properties, we want to make molecules which we can address the optical properties. And then we want to make molecules which can be switched by temperature, light, or magnetic field with two electrical properties in order to make memories, molecular memories. And then because when you go from one state to the other one, you have at the molecular level a change of the volume. So then, because this switching is controllable by temperature, light, or magnetic field, that means that you can control the volume change, and then you can have the muscles, the artificial muscles, you can have motors, which you can control by temperature, pressure, or magnetic field. So then, to do this, I mean to make molecules to solid state physics, to integration into devices, we need a multidisciplinary group. So then the group in Toulouse, it's 4 permanent people, myself, Gabor Molnar, who is doing the solid state physics of these materials, William Nicolazzi, who is doing theory, and Lionel Salmon, he is here, he will give you a talk concerning the chemistry, and then he is dealing with the chemistry in the group. Of course, we have several PhD students, postdocs, and technicians. So then, as I was telling you, what we want to do is to have molecules, okay, If you look at the energy of these molecules, it's a double well potential, and because the energy gap between the low spin state of the molecule and the high spin one is small enough, it's around kT. That means that you can switch from one state to the other one by application of temperature, pressure, magnetic field, and light. Okay? So then when you go from one state to the other one, because you are switching your electronic properties, you can see a drastic change of the color of the materials. You can go from white to yellow. You can also have, so then a volume change. Why? Because when you go from this spin state of ion to molecule to this one, here you are populating the antibonding orbitals. And then the volume of the molecule is bigger when it's in the high spin form than in the low spin form. And then you can see a change of the volume of the molecule by 13%. That means that if you can control the switching of the molecule by light, temperature, or magnetic field, you can control the switch of its volume and then mechanical properties. And also because you are going from the low spin state to the high spin state, where you have two different electronic levels and vibrational levels, so then you can also see a change of the dielectric properties of the systems by around 12% when you go from one state to the other one. So then that means that you have multifunctional materials, okay, where you can switch by temperature, pressure, magnetic field, and you have several properties you can use. You can use the optical properties, you can use the volume properties, the dielectric properties, and then when you have switching from one state to the other one, if the interaction between molecules are strong enough at the solid state, you can even have a hysteresis loop. Here the kT as function of temperature. When you go from the low spin to the high spin state, if the interaction between molecules are strong enough, you can even have hysteresis loop here. Hysteresis loop means memory effect. So then at the molecular level, you can also have memory effect. Okay? So then now, in order to study these molecules, in the lab we have many spectroscopic and solid state physics techniques. You have magnetic measurements here. You have Raman and IFM and optical measurements here. You have X-ray diffractions analysis. You have the dielectrical properties and then the photonic properties. So then we have many equipments focused on this topic in the group. And then we are trying to really go from molecules to their integration into devices through the understanding of their properties. Of course, we have many collaboration over the world because you have, as I told you, you have multidisciplinary field. So then we have collaborations in physics, in chemistry, in theory. So that here between many peoples in Europe and over the world. Okay, so then if we can summarize the history of spin crossover phenomenon, I would say that there is a molecular period between 1931 to 2003 where people was working on the molecules, synthesizing molecules and understanding their properties. And then since 2004, nanoparticles periods, that means that we wanted to make nanoparticles, monodispersed nanoparticles, in order to have bigger systems with controlled sizes in order to integrate them into devices. And then you have what I can call spatio-temporal period, where collaborators and groups in the field were studying the dynamics of the effect and the spatio-temporal, the propagation of the effect on the space and as function of time. And then we have the thin film period, you know, because when we have these molecules, if you want to make integration, you need to have these thin films. And then we had many people working in the field of making films with nanometric roughness in order to make them useful for nanoelectronic devices. And then you can have also recently the hybrid systems where we try to see the synergetic effects between spin crossover and optics, or spin crossover and conductivity. It's the period where we try to see the synergetic effect between spin crossover and another property. So then Lionel will show you some examples around this field later. And then you have also, of course, the device and integration period, which started in 1998 by Olivier Kahn in Orsay at that time. So then this is for the students, so all the papers for the molecular period, which was ended in 2004 by a very nice network, European network. And then you can have a book here, Topics in Current Chemistry, which was edited by Philip Gutlich. And then you can find all the molecular properties and synthesis of these systems. So then, concerning the spin crossover systems, what we can say? We can say that when we make these molecules, so then the molecule is this part here, and then when you assemble them into by hydrogen bonds, you can have what we can say the molecular material. So then the molecular material is at the solid state, it's combination between the same molecule, which is reproduced into the crystal, and all the properties of the crystal are mainly in the properties of the molecule. So then, today, I would say that concerning the molecular properties, we know mainly all the local molecular properties of the spin crossover effect. For example, we know what is the best structure to have the spin crossover. We know what are the vibrational properties by Raman spectroscopy, infrared spectroscopy. We know mainly all the important properties of the molecular level. So then, because this molecule is bistable molecule, so each molecule it's double potential. That means that the solid state of the system, your material, is a network of double potentials. So then you have the repetition of the same molecule, and each molecule interact with the neighbors by cooperative interactions here with the origin, which is magnetoelastic origin, and then depends on the length of these interactions. If this interaction is strong enough, you can have even first order phase transition and hysteresis. And if this interaction is weak, like hydrogen bonds, for example, so then you will have only very gradual crossover. So then what we can say? We can say that spin crossover material, it's a network of double potential in interactions. And then, of course, there is work for many people here. Why? Because you need to make molecules. You need to have the switchable molecules. You can study the interactions between molecules. You can see also, you can try to follow how the information may propagate through the crystal. So then there is many applications and many studies we can do with these materials. So then, as I told you, if the interaction between molecules is strong enough, we have strong cooperative elastic interactions enough. For example, in this sample here, what you can see a hysteresis loop like that, okay? This is the proportion of high spin molecule as function of temperature. What you can see, if this interaction is quite strong, you can have very nice hysteresis loop, thermal hysteresis loop. That means that at fixed temperature here, you can have two states. the state 0 and the state 1. And the characteristics of this state, you have two optical properties, so then you can read optically your information. So then to summarize, we have a strong change of color when you go from the high spin to the low spin form. You have the volume change of 13% and the hysteresis slope of the system. So then if you wish to follow the spin crossover, that means that if you prepare your system here with the hysteresis, if you repair it here, you can see the color of the system at the macroscopic level. It's pink here. If you increase your temperature, so then you are crossing the hysteresis loop, you will see the change of color like that. So then when the system goes to the high speed form, it changes its color from pink to white. And of course, if you come back, so I mean you go through the hysteresis loop, and then you are white, and then when you decrease your temperature, the system will go to the pink color, and then the system is in the low spin form. That means that by just temperature, you can switch the optical properties of your system, and you can see all the applications you can have through these materials. So then, if we want to understand the mechanism of the spin crossover, so then if you take a system, a spin crossover system, so then as if you prepare it at low temperature here, I take here a gradual spin crossover. So then when you prepare it at low temperature in the low spin state, so then if you look at the crystal, the system is mainly in the low spin. If you look at the energy of the system, we call that its double potential, okay? This is the free energy as function of the distance between molecules. So then we say that this, the driving force of the spin crossover is the entropy. Why the driving force is the entropy? Because when you look at the energy, the free enthalpy of the system, you see that the enthalpy is fixed. The entropy, the change of entropy between low spin to the high spin is fixed too. It's 13.4 in the case of spin 2 here. If you include the vibrations, you have something like 30. So then you have this term is constant. This term is constant. That means that only your parameter here is temperature. So then when you increase your temperature here, so then we try to increase temperature, you see that you look to your double potential, you are stabilizing the high spin form like that. As soon as you increase your temperature, you are destabilizing your system, okay? So then just because you are changing temperature, so then you are destabilizing your system, everything is constant here, only temperature you have as a parameter, thermodynamical parameter of the system. Of course, if you wish to come back, you can come back, so then you decrease your temperature, you destabilize it in the other way, and then you have the switching to the low speed state. So then the driving force is the entropy here. Through the entropy and temperature, you can destabilize your system, or from low spin to the high spin, or from high spin to low spin reversibly, okay? So now, theoretically talking, if we wish to understand the mechanism of the materials, the spin crossover materials, so then we can say that we can associate to the molecule Hamiltonian in the basis of fictitious spin here. This Hamiltonian is just the description of the double potential here. This is the isolated molecule. And then when you go to the crystal, you can add interactions between molecules by your J, like Ising, like formalism, okay? And then if you look to the vibrations in both states, because we have a change of the volume, so then you have to add the vibrations through oscillator harmonic here, because the vibrations are different, the volumes are different. So that means that spin crossover materials is the addition of these three terms. It's the addition of these three terms: isolated molecule, interactions, and vibrations. Of course, for the people, for the students who want to deal with the theory of this, you can find in the copy of my slides all these publications, and then you can see how we can solve the problem in order to find the thermal properties of the spin crossover as function of temperature, pressure, and magnetic field. So then, in the case of strong interactions, for example, if we take this molecule here, we call it polymer coordination molecule. You have the iron here, iron 2 here, you have pyrazine here, and then you have here nitrogen, carbon, nickel, and then iron. So then you have 2D polymer in the surface, and then two plants here are connected by this pyrazine here. So then everything is connected, and then you have polymer kind. We call it as coordination polymer system, okay? So then the interactions between two ions here is quite strong because you have real bonds here, not hydrogen bonds. And then that means that you have strong interactions. If you look at the experimental measurements of the property of the system as function of temperature, you see that with this system you can have a hysteresis loop here. You have first order phase transition with hysteresis loop around room temperature. You see, around room temperature. So then room temperature is very important. Why? Because if we want to make applications, we need systems which works at room temperature. And in this system, you have first the crossover at room temperature here, and you have the hysteresis at room temperature. That means that we can deal with the integration of the system into devices to use the hysteresis or the switching in order to have devices. So then we wanted to switch by light these systems. Okay? We wanted to switch. We did the experiments. And I will show you that it is possible to write informations in this molecule by using 4 nanosecond laser. For example, it's exactly the same system here. What we wanted to do, we wanted to see if in the hysteresis loop here, we can switch by applying pulsed laser in the hysteresis, if we can switch reversibly the system between one state to the other one, in order to find the way how to write information in the materials. So then the idea is the following. First, we had to analyze the hysteresis loop here. If you analyze the hysteresis loop through the Ising-like model like that, like I shown you before, you see that if the interaction is strong enough, you have hysteresis loop. What is very interesting to see here is that around the Curie temperature here, you have 4 regions here, okay? You have 2 metastable regions in red here, and 2 stable regions here. Here you have the high spin form, here you have the low spin form. Because you have 2 metastable regions here with different spins, that means that, you know, when you are on a metastable state, if you apply any pulsed energy, you can push the system to go to the stable one. What is it interesting here is that you have in both spin states, spin 0 and spin 2, you are on metastables here. So that means that if you can find a way how to give energy to your system in the 2 metastables, that means that you can switch it from one state to the other one. So then to find this, we looked at the optical properties. What you can see here, the system in the high spin form absorbs in the green, as you can see here, and in the low spin form, it also absorbs in the green. That means that green light can be absorbed by the system in both states. This is one first point. The second point is that when you apply your pulse, you can try to use the laser to write your information. You need to read this information. So you need a way how to read the switching. So that if you look at the Raman spectroscopy between low spin to the high spin, you see that when you go from low spin to the high spin form, that you have switch of more shift of more than 50 wave numbers when you go from this band here, when you go from the low spin state to the high spin state. That means that if we use pulsed laser in the green, we can send our energy. If we can use also a Raman to read the switch, and then we are ready to make the applications. So then we did it. So that what we did, you have your sample here in the cryostat at fixed temperature, room temperature, and you have two lasers, one for the green laser here to send your pulse, to send your energy, and the other laser here is to read by Raman spectroscopy your switching. So you send, you probe, and read, okay? So then, if you look now at the experiments, what you can see here, okay, when we are here in the point A, as I told you, we are in the metastable state, low spin state, okay? If you look to the Raman spectroscopy here, low spin state is characterized by one peak here, Raman band here, and nothing in the high spin form. If you send your pulse, you go from this point to this point. If you send your pulse at the point A here, you go from this spectrum to this one. You see, the low spin state disappears completely, and then you have the appearance of the high spin form. And what you can see is that the switching is complete. Here you are 100% low spin, and here you are 100% high spin. That means that you went from the point A to the point B, from low spin to the high spin, by sending only one pulse, 1 4 nanosecond green pulse. Now, could we do the switching in the other side? That means that you write and you erase your information. So then, when we are in the point C here, you see the Raman spectra here, the spectrum is high spin form, without any low spin signature here. When you send your pulse, you go from this spectrum to this one. You see, the high spin disappears completely and low spin appears. That means that you go from completely high spin, like here, to completely low spin, so then you are going to here. So that means that with two pulses, 2 4 nanosecond pulses, the first one you can go from the point A to B, you write your information from low spin to the high spin, from 0 to 1, and the second pulse you go from high spin to the low spin, you go from the state 1 to the state 0. This is the demonstration that at room temperature we can address these systems by using just two pulses, okay? So then after this, because we know how to write informations in these systems, we started to make nanoparticles. Why we started to make nanoparticles? This is in order to have systems which we can integrate into devices. So then, just very quickly, so Lionel Salman will show you the chemistry of how making these nanoparticles. Just very quickly, we use the missile, the reverse missile technique here, where we prepare in one side you have your iron salt, and the other side you have the ligands or the other components, and then in the micro or nano reactor here you can make your reaction, and then you can have your particles, and then you can play with the size of the particles, 2 nanometers, 100 nanometers, and then you can also play with the shape and the form of these particles. You will see that this will be very important for the integration, for making devices. So Lionel will show you the synthesis and making, and how we can make these systems. What I would like to tell you here is that through this preparation, because we prepared spin crossover nanoparticles, so then we can study the effect of the size of the molecules on the hysteresis loop, on the memory effect. Why we wanted to do this? As I told you that molecules are interacting between them. So the number of molecules is important. If you decrease the number of molecules because you are decreasing the size, so then you can lose your hysteresis loop. So then what we have seen that this is the bulk. You have a lot of interactions and then you can have hysteresis loop. When you decrease to 120 nanometers, because you are cutting your interactions, your elastic interactions, so then you can decrease completely, you can decrease your hysteresis loop. What is interesting here is that when you go further to very small particles, you see that you have a hysteresis loop appearing at very low dimensions. And for us, it was very surprising to have hysteresis at nearly few molecules. And then the idea comes from Moss-Bower spectroscopy, where we studied the elasticity of these systems. What we have seen is that the surface may have elasticity which can be a lot of higher than the bulk. When we go to very small dimensions, we have the elasticity because of the surface effect diverging. And because the cooperative interactions are elastic, if you have something increasing the elasticity because you have surface effect at very low dimensions, you have only surface here. So then you can make a reappearance of your hysteresis loop. That means that at very low dimensions, 2 nanometers or 1 nanometers, you can have a hysteresis loop. Okay, that means that you can go in your integration at very low dimensions and to try to have high density information storage. So then, and after this, because now we know how to address them to make this molecule, we wanted to study the phenomenon, the physical phenomenon of the spin crossover. So then, you know, when you have materials, when you switch your temperature or light, you go from low spin to the high spin. And the question for physicists, it was how the system behaves. Do we have a random appearance following Boltzmann statistics of the high spin form, because you are switching, or you have something like nucleation and growth. That means that you have size, 1 pound, 1 molecule, 1 place where you have the switching, and by neighbor to neighbors, through nucleation and growth, you have all the system converted. It was the question. So then, if we use the Ising-like model, as I shown you, and if we can solve it through the crystal, what the model tells us? The model tells us that when you go from the low spin to the high spin, you can go through nucleation and growth process. Okay? This is the model. And the question it was, could we make demonstration that when we switch our system, we are going through nucleation and growth. So then what we did, we took crystal, just 1 crystal, through a microscope in a Raman spectroscopy, and we did imaging on the crystal. So then here are the Raman spectra, the imaging by Raman spectroscopy. We said that when we have the band of low spin, it's yellow. When we have the band of the high spin, we give the pink color. You see, when we are in the low spin state here, everything is low spin. So then when we make the imaging by Raman spectroscopy, we can see spectroscopically that your surface is in the low spin state. When you increase your temperature here, you see the appearance of the high spin form here. And when you still decreasing your temperature, you see you are increasing the domain of the high spin form till reaching all the crystal. So then by Raman spectroscopy, we could demonstrate that the spin crossover phenomenon on the crystal behaves as nucleation and growth phenomenon. And then we wanted to see this. We wanted to check if optically we can follow this. This is the same crystal through crossed polarizers. And then we wanted to see if we can see the switching optically. This is the real experiment through the microscope. And you see here, we wanted to check this process. And as you can see here, the system is completely red in the low spin state. When we have the crossover, you see, we can see that we have this nucleation and growth through the crystal. And then the second point, we wanted to see something. So then we took our crystal, okay? We, as you have seen, you have the nucleation and growth. We can see it, okay? And then we said, what happens if we can put a defect here, just here? By laser ablation, we put defect. What is the effect of the defects? Because our interactions are elastic. That means that the strain, the local strain, and the defects may have an important role in the nucleation and growth. So then, we took exactly the same crystal, same nucleation and growth, and we put a defect here. And we tried to make the experiment. As you have seen in the beginning, without the defect, you have the nucleation and growth in this direction. It goes from this part to this part here. And now here with the defect, just check here. You see? So you see? So the direction of the nucleation and growth is inverted. It started through the defect, and then it's completely inverted the directions. That means that at the beginning, we have our propagation in this direction. Because we put a defect here, we changed completely the propagation. That means that the nucleation of growth, of the spin switching on the crystal can be modified by applying artificial defects. And even we have some work now, we are working on the form and the shape of the nanoparticles to see that we can have very nice physical properties, very nice kinetic properties. We can play with this nucleation and growth, and we can even control it by applying some intelligent defect in the system. This is a very important point. So then after this started, of course, the thin film period. Because as I told you, you have seen how we can make these molecules, the phenomenon, how we can have addressing of these molecules. You have seen the nanoparticles part, etc. You have seen how we can follow the kinetics. And now we need integration. We need integration, that means we need to control the films, how to make films. So then, as we took the same sample here, okay, and then as I told you, for chemists, the question of making thin films, the crucial point is how you can fix your system in the surface. So then many people was trying by using several techniques in order to have these thin films. Always people, they can have the spin crossover, but they lose the cooperativity. They lose the hysteresis loop. So then, if we take this one, it was the first time that thin films could be done in 2006, something like that in the group. When we look to this material here, what we can see, you have pyrazine here, okay? We have a ligand called mercaptopyrazine. Mercaptopyrazine is exactly the same ligand here, but instead to have iron here, you have sulfur, okay? You know, sulfur likes gold. It fixes very well on gold. And then what we said, why we don't take mercaptopyrazine, we fix it on the surface, and we try to make layer by layer sequential synthesis slowly to try to fix these materials on surface and try to see if we can maintain our hysteresis loop, okay? So then it's exactly what we did. So then we took mercaptopyridine, we fix it on the surface, we bring the iron salt, okay, and then the iron platinate, and we come back with pyrazine. And as function as you turn sequentially, layer by layer, you are growing your system, okay? What you can see with this technique, we can have very nice thin films, as you can see here by electron microscopy. So then by playing with all the parameters of the surface deposition, I mean concentration, temperature, etc., you can increase the quality of your surface, we can have even 7 angstrom of the roughness, which is sub-nanometric, which is very nice, very interesting. And Lionel will tell you about the chemistry we used in order to increase this. So then that means that today we have our thin films, and of course what we wanted to do, to use e-beam lithography, because we have in Toulouse nanotechnology platform, and then we used combination between layer by layer synthesis technique with e-beam lithography in order to have something like that. So then you have nanostructurations, you have dots, okay? It's the surface which is nanostructurated. You have 30 nanometer of each dot here, okay? And then you have very well organized surface, and each dot is spin crossover dot with maybe hysteresis. Because the question is, do we still have our hysteresis loop at 30 nanometer, okay? So then, of course, we have this very well organized surface, and then we have 30 nanometer here. The spin crossover here of the dots is between low spin state, spin 0, diamagnetic, and the high spin state, spin 2, paramagnetic. Today there is no machine can measure the magnetic properties of one dot. It's very complicated because you have very low change of magnetization at 30 nanometer. So then we wanted to see if we can find something in chemistry in order to measure if we have or not this hysteresis loop. So then, and then started the hybrid period. The hybrid period is to combine, for example, spin crossover materials with luminescent systems and try to find if we have any synergy. You will see that by using a combination between spin crossover materials and luminescence, we can read the change of the properties in our dot and see that if we have or not the hysteresis loop. So then what we did the following. If you take this spin crossover system here, if you look at the optical properties of the spin crossover, in the low spin state, it's pink here, it absorbs in the green region at 430 nanometer, okay? In the high spin form, it's transparent, so then it's transparent, there is no absorptions. So then, if you take the rhodamine, which is another complex, which is luminescent complex, if you look at the optical properties of the rhodamine, you see that the emission of the rhodamine, it's exactly at the emission is here, it's exactly at 430 nanometers. What this means? This means that if you combine in the same material, rhodamine and the spin crossover, if the system is in the low spin state, it will absorb the light of the rhodamine. But if it's in the high spin form, it's transparent, light is not absorbed. That means that through the spin crossover, you can quench or not the luminescence of your system. And you will see that through here, so then we did this synthesis, so Lionel also will explain how we can make this systems by combining, so then the rhodamine here to make a hybrid system. What you can see now, when we combine to our dots the rhodamine in the system, here you have the system in the low spin form. In the low spin form, as I told you, it absorbs the rhodamine light. Here in this situation, the light is absorbed. Now if I try to hit the system from low spin to the high spin is not absorbing. That means that we will see all the light of the rhodamine, as you can see here. Here, we are in the low spin, always low spin. The high spin is around 50 degrees. You will see, here we have the crossover. Okay? You see that light is all absorbed or it's released through the spin crossover. That means that you can make the switching by temperature of your crossover and you can quench or not your luminescence. And now we can follow through the luminescence only one dot. what you can see here, this is the fluorescence as function of the temperature. It's only one dot. What you can see that one dot, 30 nanometer dot, may show you a hysteresis loop. That means that 30 nanometer, you can measure the property of 30 nanometer dot, and it shows a hysteresis loop. Okay? So, of course, concerning the application, you can have many applications through there. Why? Because what we need today, we need micro or nano thermometry. In biology, for example, we need to measure temperature as function as time, but also spatially resolved. We need to know at nanometer scale the temperature to follow the several mechanisms we have in electronics or in biology. What you can see here, for example, here we take wire, film on the wire, so then by current we can have temperature changing like that. You can see that you can follow through the spin crossover the switching of the luminescence. What you can see also here is that when you take wires and then bridged by two conductors here, wires like that, the space between wires is nanometric. You see that your system can reveal at the nanometric scale the temperature. Here it's, for example, where it's luminescent, it's cold. When it's dark, it's hot. That means that you can follow the temperature at the nanometric scale, spatially talking. Okay? And you can have many applications with this kind. So, and then the period of integration started to make devices with these systems. As I told you, by using the micro-measure techniques, we can have several forms of our nanoparticle. You can have also rods here, so that we will use them in order to follow the electrical properties of these systems. By using dielectrophosis, that means that you take your nanoparticles between two electrodes with electrical field. You can organize your rods between two electrodes. You can see if you work well, you can even select only one rod between electrodes, and then you can study the electrical properties of the system. And now we can study the electrical properties of the systems. What you can see is that we can have with one rod beautiful hysteresis loop here. Hysteresis means memory, okay? So then we are dealing now to study the electrical properties of these systems through this approach. And then we can also make something, we can work with junction. Junctions means we can take a spin crossover system here between aluminum, ITO, and then try to see the transport through the spin crossover. For example, if we take the 30 nanometer size, you can see here, for example, if you have the spin crossover system here, okay? If you are in the low spin state here, okay, you go to very low temperatures. If you send your light, you switch your system from the low spin in dark and low spin by irradiated. You have a photocurrent here. And then because the system can be switched from low spin to the high spin by light, least effect, okay? That means that by using light and the junction, you can compare the low spin irradiated and the high spin irradiated in the same systems. And what you can see, you have big difference of the conduction between the low spin and the high spin. That means that the value of the current in your systems depend on the spin state. It's kind of spintronic molecular. That means that the transport in the system, in our system here, depends on the spin state of the systems. So then the current is not the same if you are in the low spin or the high spin. That means that you have something dealing with what we can call the molecular, kind of molecular spintronic. So then the last part is the volume change. So then we wanted, as I told you in the beginning, to use these materials in order to use the volume change. So the idea is the following. If you take your system, if you look to the structure of your system, when you go from low spin to the high spin form, you have the change of the volume by 13%. Okay? This is just classical structural analysis by X-ray diffractions. And then what we wanted to do, because of this volume change, we wanted to see if we can use this volume change. The idea is the following. We made a bilayer like that. Here it's gold, as you see here. On it we can fix our spin crossover system. And then you have the bilayer system. When you have a bilayer system, when you have one layer which wants to change its volume, and the other one it's fixed, because these layers are fixed, so then when you switch your system from one volume to the other one, you expect to have actuation, okay? So then what we expect here, we expect to have, when you have the spin crossover of this layer, we expect to, we expect to have something like that, okay? So then here we are in low spin, here we are in high spin form. So then why? Because we have a bilayer, and then you have one layer which wants to change its volume, the other one is inert. So then through the spin crossover, you expect on the paper to have this actuation, okay? So then we try to do it. So then we try to do it as you can see here, okay? Okay, we put our bilayer, okay? And then we changed the temperature to make the spin crossover. What you can see, you have your actuation following the change of temperature. That means that now we have how we can control the sense of the motion, okay? We are converting energy, thermal energy, by changing temperature into motion. But what is important here is that we can control the direction of the motion through heating or... and of course, the idea is the following. By temperature, light, magnetic field, try to have the motion and conversion of energy in order to have nanometric motors using this phenomenon. And of course, we did this experiments as function of light. You see here, the system, when it's in dark, it's in this position. When it's irradiated, you have another position. That means that if you irradiate, with fluctuation of your system by light, sinusoidal light, so then you can control the motion. So then you are converting your optical energy into motion. So then this is the recent work we did in Toulouse by Dolores Manrique. She is the Mexican PhD student in the group. So then we tried to combine between the actuation and the color change. You see here, you see, when we change our temperature by in this form like that, so you can see that you have your actuation, and because you have the spin crossover, you have even also the change of the color. You see, pink to yellow, pink to yellow. So that you have two positions, mechanically talking, and you have two colors. That means that we can have our actuation, and then we can have the color change for the sensing. That means that we can combine the actuation and the sensing through optical properties. And if you want to have artificial muscle, you need the actuation, you need to control the sense of your actuation, and you need to sense, to have sensor on your actuator in order to see in which position you are. So then this is a very recent result, which is quite beautiful result we got just recently in the group. And then, of course, we wanted to study deeply the mechanical properties. It was the PhD thesis of Edna in the group. By using IFM, we wanted to see the mechanical properties of this system. And if you look by using IFM techniques, we can see that the Young modulus may change from the low spin state to the high spin state by 30% around. That means that at the intrinsic properties of your systems, these systems can be used for working because they have intrinsic change of modulus Young. So then you can compare, for example, if you look at the work density of your system, of many systems, you have the spin crossover here, you have the human muscles here, you see that what we can see that the spin crossover systems can be very nice materials for to use them as systems for work density. You can see also the change of the speed of the response of your system. Here you are macroscopic, here you are nanoscopic. At the nanoscopic materials, they can be very quick, so then the response can be quite quick. So then, in order to simulate the muscle, as you can see here, we took a wire, and then we put around the wire our material, and then if you send your current through the wire, you can expect to have the crossover and actuation, and then what you can see here, okay, we took macroscopic wire, okay, you see, by changing temperature, you see, you can have your actuation. It's quite slow, but at the macroscopic level, we know that it's slow, but it's working very well. So then that means that now the, sorry. Sorry. So then our idea now is to try to work with real muscles. The idea is to try to correct some defects in the human muscles, and we are trying to integrate these systems in order to have real systems working in real applications. So then just to tell you that you see multidisciplinary approach between chemistry, physics, nanotechnology, and theory. We can deal with many and beautiful work, and then the interdisciplinary between chemistry for the materials and physics to study the properties and nanotechnology to integrate. We can have many exciting things. Thank you very much for your attention.
En francés. Si quieren hacer un par de preguntas antes de pasar a la segunda plática del doctor Lionel Salmon. Por favor.
Two questions about the experiments of conductivity. First, can you change the molecule from one state to the other with the current, or maybe with the spin polarization of the current?
Yeah, we can change the structure of the molecule, yes, by current. Yeah.
By the current, from one state to the other?
Yes,
yeah. And does the different conductivity depends on the molecule itself, the intrinsic property, or simply the different hybridization at the contacts with at the junction with the contacts?
This is a quite good question. I think it's both. We have both possibilities. But you have the contact which bring, of course, which is a key parameter, and you have, in our case, in the case of our molecules, the structural properties of the molecules can have an important effect, because when you have the switch, you have also the switch of the structure, and then the electronic levels, and everything changes.
And the switch of the contacts.
And the switch of the contacts, yes.
The switch of
Yeah, yeah.
Otra pregunta.
Go ahead in French. It's better.
Well, this,
Yeah, go ahead, go ahead.
can be used in buildings.
In what, sorry?
Can be used in buildings.
Buildings, what means? Oh, yes. Oh, yes. Yes, of course. Yeah, just, you mean in the construction, in the materials? Yes, of course. Yes, of course. We have 2 contracts around that already. And there is many possibilities. Why? Because first, in the buildings you need glasses which where you have transmission of temperature depends on the color of the glass, switchable glasses, okay? This is first application we are dealing with. The second one, as I told you, we have first order phase transition. When you have first order phase transition, that means that in the first jump, you are exothermic. In the second jump, you are endothermic. So then you have hysteresis in transmission of heating. Now, for energy economy, if we make building with hybrid between our materials and the normal materials, so then you can see that you have inertia between the temperature you have outdoor and in the room, and we can have many energy economy, and we have already a contract around that in order to have smart buildings.
Otra pregunta por acá. Pero no tenemos un micrófono.
Merci. À la section laquelle vous faites de mesure avec la rhodamine, le spectre de l'absorption,
Oui.
la switching avec la jonction, est-ce que ce méthode de convertir de l'énergie au système ne fait pas la transition de l'haute spin au basse spin? Does this inserting of energy by light on rhodamine not make the switching occur as well?
This is a good question. You mean switching by light? Yeah. No, because you are at room temperature. The switching by light, you can do it at very low temperature. At room temperature, the kinetics, the relaxation is very quick. Okay? That means when you switch, it comes back quickly. So that means you will not see any switching by light. You will see only the thermal effect, okay? Because you are at room temperature. This is good point. You see? If you want to have switching by light, okay, you have 2 possibilities. Or to go very low temperatures. If you want to use low power of your light, okay? Just normal light, green, laser, etc. You can have the least effect. You switch to the high spin form, and because that the relaxation is very slow at the cryogenic temperature, you are pumping your system, and then you can keep your system in the switching state. But at room temperature, if you want to have switching by light, you need some typical conditions. That means that you need to be at the Curie temperature, and you need strong energy, optical energy, in order to switch it. Otherwise, no way. The relaxation is very quick. Good question. Thank you. Yes. Yes.
Good afternoon. You said that you want to store information and then you retrieve it. You, well, in your presentation, said that Raman, it was
Yes.
a way. But, well, if you want, I don't know, spintronic or any other application, it's very difficult to have a Raman that can do it in an application stage.
Yes.
So there's another way to retrieve information. Have you done or think another way to do it?
Yes, by the dielectric properties. Today, the nanotechnology people, they are working with crossbar techniques, yeah? When you have crossbar, at the point where you have the cross, you can put your current for heating, but you can measure the dielectric properties of, you have a capacitor, as I told you, you have a change of the dielectric constant. That means that by measuring the capacity of the point, you can see in which state you are. So then you can electrically read your information without using any optical. The optics I have shown you, it was for me to demonstrate that the switching is possible and study the spectroscopy of the effect, because we want to understand the mechanism through the hysteresis loop, etc. But if you want just one temperature, just one switching, you don't need light. You use just crossbar, electrical and dielectrical measurements, and that's it.
Okay, thank you very much.
Okay?
Ok. Bien, sería la última antes de pasar. Ah, también.
What do you think of the result of the elections in France in general and in Toulouse in particular?
I am sorry, I know my field better than the elections. It's very strange, the situation, you know. I know the result.
And in Toulouse, you know the results?
No.
Yeah?
No.
Okay. Mélenchon was first in Toulouse.
Oh, that's good. That's good. That's good. Mais j'ai pas vu pour Mélenchon. This is good news. Thank you. But Mélenchon. Bizarre. Très sûr.
Well, I have a question about, have you tried any in vivo probes in...
Sorry, go ahead. Yeah, go ahead again.
Okay. Have you tried any in vivo probes of your compound? Trying to join this molecule to a bone or some tendon to use it as a artificial muscle?
Yeah. So the artificial muscle is just starting. For me, for the artificial muscles, all what is done in this field is here. Concerning the spin crossover, we tested first the actuation, the thin films, and check what are the properties. And I think all the chemistry of artificial muscles is in the future. We don't have nothing at the moment. We are just starting. What we can say is that we have very important and potential properties, and then the field is quite open now to go further. But we have not yet chemistry in this field. Yeah.
Okay. Bien, bueno, vamos a pasar a la plática.
Thank you very much.
Salto.
Bien, vamos a continuar con la segunda plática. Ok, la segunda plática la presenta el doctor Leonel Salmón, que son, la plática se intitula Materiales de transición de spin y nanomateriales. Muchas gracias.
Thank you, Pilar. So, good morning, everybody, or good afternoon, maybe, I don't know. So, I will switch to synthesis. I will show you how to synthesize spin crossover materials and to elaborate nanoparticles based on these materials. Okay, so I switch this slide because now we know, everybody knows what is spin crossover materials. So I would like just to come back on this slide concerning the interaction between molecules. So as it is said, as a function of the interaction between molecules, we can have different behavior. So when we have weak interaction between molecules, we have quite gradual and sometimes incomplete transition. And on the other end, when you have strong interaction between molecules, it's possible to have hybrid transition and hysteresis loop and even transition different steps. Okay, so I would like just to illustrate this different behavior, showing you example of spin crossover materials. Okay, so we will study this family of complex. So it's a mononuclear substituent on the aromatic rings. Okay. So here's some example of substituent on the amine and on the cycles. So this is a structural determination of one of these molecules. Here you can see the methyl group here by the tetramine, and the nitro and the methoxy group here by the aromatic rings. Okay, so now just a little bit synthesis. Here you have, here the synthesis of the ligand. So it's just a reaction between two equivalent of salicylaldehyde with tetramine in alcohol, and you obtain this sheaf-based ligand, so with formation of two imine, okay, here, and using a particular iron salt with sodium hydroxide for the deprotonation of the hydroxide, we can obtain the corresponding complex. Okay? And of course, we can obtain, modifying, as I told you, a family of complexes. So here is one of these compounds of this family. So we have the methyl group in the central amine, and in the aromatic cycle, we have two substituents, the methoxy in the 3 position and the nitro in the 5 position. Okay? So now, if you look at the spin crossover properties, we can observe small things here. So chi T equal to 3 correspond to the high spin state. And what we observe is just a very gradual and very incomplete spin conversion. It's not a spin transition, it's a spin conversion, okay, for these materials. So we try to correlate these properties with the structural parameters of this complex. Okay, so this is a result of the structural determinations. So here we can see that the molecules are aligned along chains. And in this case, there is only one weak contact. It's a weak hydrogen bonds, hydrogen interactions, okay, with a distance of 2.7. It's very weak, also with very small angles. So it's one very small contact between molecules. And as a consequence, so you have a weak hydrogen bonds, and then you have a gradual and incomplete conversion. So we have a relationship between the structural property and the spin crossover properties. Okay, here we can also observe the classical metal ligand distance of 2.1 in the high spin state. Okay, here at 180 K. Okay, now we modify a little bit the ligand using chemistry, of course. Here we can see you just change the methyl group. Here you have now protons, okay, an hydrogen, and then if you continue the study, you look at the magnetic properties, and now you can observe a very nice spin crossover with an hysteresis centered at about 120 K. Okay? Again, now if you try to have the correlation, we understand. Here now we have so the same geometry, same structural organizations, and now we have 4 not strong interaction, but you have 4 hydrogen bonds in this kind of molecules. So this can explain the abrupt transition in these complexes. So when you have a stronger hydrogen bond network, we obtain complete and abrupt transitions. Okay. So of course, if I come back, and like as it said, this temperature is not very useful if you want to go to other applications. So the motivation is the following, is to have a hysteresis loop or transition temperature centered at room temperature, and as a function of the application we want to reach, it's necessary sometimes to have hysteresis loop. Okay? So this is a nice example. This was already described by Azedine. So just so you know, we know now that we have planes with iron here, which is active centers. And these iron are bridged to other metals, in this case is platinum. Okay? And these planes are bridged by the presence of this monodentate ligand, in this case the pyrazine molecules. Okay, so concerning the property, now you know already that we have a very nice spin transition at room temperature, and we can observe here the color change of the samples. Real and Kitazawa observed also that this kind of material are sensitive to the inclusion of guest molecules. Okay, so here, for example, we can see the inclusion of CS2 molecules in the packing of these three-dimensional systems. And they have demonstrated bidirectional chemoswitch. This means that here in blue you have the empty complex, and if you are in the low spin state here, so with the red color, and if you expose the sample to benzene, you will have a switch of the sample from the red to the yellow color. So we can follow, okay, just by optics, the inclusion of benzene molecules in these materials at room temperature. And you have also the reversible process if you are here in the high spin state, and then you enter CS2 molecule in the system, you will switch back from the orange to the red color. So we have demonstrated this bidirectional chemoswitch. Okay, so in the group we have developed this chemistry, and for example we have used these BPAC molecules, which is longer and more rigid ligand compared to the pyrazine. And so we have obtained similar organization, so we have always these three-dimensional systems. And what is interesting here is that you have the volume of the pores, which is 48%, which is twice the volumes for the pyrazine derivatives. So, like this, we can increase both the cooperativity, but also the porosity in these three-dimensional systems. Here we can see that using this BPAC, in fact, which is a bridging ligand of the three-dimensional structure, this molecule also enters in the cavity of these large cavity complexes, let's say, okay? And thanks to pi-pi interaction between the aromatic cycle of the bridging ligand and aromatic cycle of the guest ligand, okay? And we will see that the quantity of BPAC molecule, of included BPAC molecule, this one, will be very important for the spin crossover properties. There will be a correlation between the quantity and the spin crossover properties. Okay, for example, if you add the platinum to the ligand and the iron salt, this means we have an excess of the ligand. We obtain this formula with a large quantity of BPAC molecules. Okay. Now, if you look at the properties, we have, so we realize two steps. The first step, the two cycles, is T versus T, okay? So we realize two thermal cycles. The first cycle is a black one, so we have no hysteresis. And when you heat, in fact, you remove solvent, including the molecules, in the complexes, and then you obtain these very nice red cycles with about 70K hysteresis. Okay, so use also Mossberg spectrometry to see if the transition is complete or not. Sometimes with magnetic measurement, it's difficult to see if we have a complete transition or not. With Mossberg, it's very clear. For example, here at 410K, so we are in the high spin state, the spectrum contains only one doublet with a large collision splitting and an isomer shift of 1. This doublet is characteristic of an high spin state. Okay? When you decrease temperature, so now we are here, far from here, at 80K, so we are in the low spin state. Now this doublet disappears, and you have the appearance of this doublet with a small collision splitting. This means the distance between the two peaks. And this isomeric shift of 0.5 is characteristics of a low spin state. So using Mossberg spectroscopy, we can definitely say that we have a complete spin crossover in this complex. So you have complete transition and a very nice hysteresis loop centered at room temperature. Now, if we change a little bit the experimental conditions, here, for example, you add, so you invert the reaction, you add the ligand to the platinum salt. Of course, you have no excess in the medium, sorry. And then you obtain this composition with of course, you decrease the quantity of the PAC molecule inserted in the three-dimensional systems. Now, if you look at the properties, you have a completely different behavior. So, again, you have two thermal cycles. So, the black one is the first one, so you have no hysteresis, and an hysteresis for the second one. But you observe that you have approximately half transition. So, this means by only half 50% of the ion center transit. Okay? Using Raman spectroscopy, it's also possible to see the free BPAC here. So with this method, you have less free BPAC for the method 2. Okay? And you can also see the presence of the bridging ligand here. Okay, so again, we try to correlate this different behavior with the structural parameters of the different complexes. So again, using Mossbauer spectroscopy for these samples with a small quantity of inserted BPAC molecules, we obtain in this case two high-spin doublets. Okay? The green one with the large polypore splitting, which means the distance, corresponding to an axial compressed iron 2. Okay? So in fact, you have good reason to think that the rigidity of the ligand can be accommodated by the network by a dissymmetric coordination leading to two different iron centers. Okay? Oh, sorry. Two different iron centers and the compressed one, so the green one here, behind spin crossover inactive. That's why we have only 50% transitions in these materials. Okay, so to go further, you expose these powder materials, powder complexes, to vapors of pyridine. Okay, so we let the sample overnight at 35 degrees. And we check the uptake of the pyridine using TGR coupled mass spectrometry and Raman spectroscopy. Using Raman, again, it was possible to see the entrance, the inclusion of the pyridine. Okay? And using the mass spectrometry coupled TGR, it was possible to estimate that we have about 0.7 pyridine per ion centers. Okay, again, we look at the Mossbauer spectroscopy for this compound, including the pyridine molecule, sorry. And in this case, we can observe three different high-spin doublets, which can be explained as follows. So the pyridine enter in the structure and tend to decompress the systems thanks to pi-pi stacking interaction between the BPAC and the pyridine, sorry. And in agreement, which lead in agreement with the Mossbauer spectrum, with three different ion centers, depending on the vicinity of the ion and the number of pyridine entering the systems. Okay? As a consequence, so as expected, we increase the quantity of decompressed ion, and then when we look at low temperature, you have an increased proportion of iron 2 presenting spin crossover properties. This was also demonstrated by magnetic measurements. Okay, so this is without pyrazine, this with pyrazine. So the quantity of included of spin transition molecules increase. The presence of the two steps is related to two different centers as a function again of the vicinity, because some have BPAC in the proximity and the other one have pyrazine. Okay, so that's why you have a two-step spin transition. Okay, so until now I've shown you that it's possible to have room temperature crossover, and that this material can be useful for gas sensing. Okay, but if you want to go further and to go to our application, it's necessary to have nano-sized object of these materials. Okay, that's why now I want to switch to the elaboration of a nano object. So why? First thing is for fundamental reason, to see what will be the effect of the size reduction on the spin crossover properties. So what will be the effect on the hysteresis loop? Okay. What will be the effect of surface? Okay. When, as it is said, that when the nanoparticles decrease, surface will be more and more important, of course, and then we will have a surface effect. This part of elaboration of nano-object can be also useful for the synthesis of hybrid materials. So we'll see some example later. And of course, again, to go to other applications. So we have seen this morning application in the field of molecular actuators thermometry. Okay, so now how to obtain this kind of nano-object? So we develop two strategies, thin films, and an extension is the pattern, so we'll see example, and also synthesis of nanoparticles. So we are here in the domain of nanoscience. Okay, you know a little bit this slide. So just I want to go into details concerning the synthesis. So in fact, as Ine said, we can use the mercaptopyridine, but you have improved more these anchoring molecules. In this case, always use this disulfur, and this branch is used in order to separate the pyridine function. And this is more in agreement with the three-dimensional system of the morph you use. Okay? So this is an improve of this kind of depositions. So you start from gold substrate, you functionalize, and then you using layer by layer techniques. This means first you attach iron, then you attach the platinate bricks here, and then the pyrazine, and you can repeat this kind of experiment to have to improve the thickness of the film we want to obtain. Of course, this is not very simple. Seems to be simple here, but you have to. We have to control a lot of parameters. So I speak about the anchoring layer, but you have to determine the good sites, the concentrations, also the dipping time, the number of rinsing steps. So it's not very easy. So we spend at least 3 years to have very nice films of this kind of components. So we already saw this, so we can obtain roughness which is less than 1 nanometer. So on this large area of films. So the extension of the formation of films is to obtain patterns. So for this, we combine this layer by layer assembly with with E-beams. Okay. So for that, we deposit a conventional PMMA polymethyl methacrylate resist on golds. Okay. And on this resist, we write patterns using a focalized electron beams. Okay. So, but we did, in fact, you modify the solubility of the resist. And then using an appropriate solvent, you can remove the irradiated part of the resist. Like this, we have these patterns. And using this film, in this pattern, you can, again, realize the layer by layer assembly. Okay. So in fact, we attach, here we have sulfur, of course, anchoring layer. So using another solvent, you have this lift-off step, and that way we can remove the obtaining pattern of these different materials. So it's possible to obtain different size and also different geometry. Here just an IFM measurements. Here we can follow. So these dots correspond to 15 deposition cycles. Normally the theoretical value from one cycle is 0.7 nanometers each layers. So if you multiply 15 by 0.7, you have we found about 12 nanometers. So you have very nice deposition. It's like epitaxial growth, in fact, of the films. Okay, just very fast, we have also demonstrated that using these patterns, it's possible to have the gas sensor effect. Okay, like before for the powder, you have the same effect when for the inclusion of pyridine. So you have, again, the increase of the active species and the modification of temperature transition. Okay, so now I want to switch to the other part for concerning the elaboration of reduced size objects. So I will speak about the elaboration of nanoparticles. Use different strategy, again, homogeneous media and heterogeneous media, and mainly the reverse Meissen methods. Okay, so just what is reverse Meissen, just in case you don't know. So reverse Meissen is liquid polar droplets stabilized by a surfactant in a wall phase. Okay? So you have a ternary system, polar medium, okay, here, the surfactant, which has hydrophilic heat, okay, and a hydrophobic tile, okay, and a oil. This is, for example, one example of surfactant. So here you have the polar heat and the hydrophobic tile. So the idea is to control the size of the micelles, okay, playing with the concentrations of the surfactant, the water, and the oil, okay. You play often with this omega parameter, which is a ratio between the water and surfactant quantities. Of course, you can also change the temperature, And changing all these parameters, it's possible to control a little bit the size of the micelles. Of course, this micelle will act as a nanoreactors. So we want to confine the growth of the material inside the cavity of these micelles. Okay, this is what we did. We have seen already this slide. So we prepare two independent microemulsions containing pyrazine and iron, and the other the nickel, for example. And after a micellar exchange and fast stirring, we obtain, so we grow the nanoparticles inside the micelles, and the growth is limited, of course, by the size of the micelles. So we obtain these type of microemulsions, and using centrifugation or evaporation, it's possible to obtain powder containing spin crossover nanoparticles. So modifying the concentration, we can have different size from, for example, 100 nanometers to 2 nanometers. Here is the characterization of the nanoparticles using, here you have dark field team pictures. So if you analyze this part, okay, we can find that we have well iron and nickel, which compose the clatrates. We have about 50-50, which is what we expect. We can also realize map, confirming that we have well at the same position iron and nickel. This confirms again the composition of the two-dimensional system. Using this X-ray, energy dispersive X-ray analysis, it's possible to probe only one small nanoparticle. So even for one particle of about 2 nanometers, it's possible to have this quantity. So even if the small nanoparticles, we have the good composition. Okay, so now if you look at the property of these different samples, different particle size. So for large nanoparticles, of course, we have a lot of molecules, so you have big interaction. So as expected, you have a spin crossover with hysteresis at room temperature. When the size decreases, for example, at 10 nanometers, as expected, we have diminution of decrease of temperature transition, and the cooperativity decrease. Okay, we have no hysteresis loop, and we have a gradual transition. Okay, this is expected because we reduce the number of ion centers. So you decrease the cooperativity, and you have gradual transition. This is very new and not expected for these 2 nanometer nanoparticles. This was predicted by theoretical calculation, but for the first time, it was possible to observe that for such small nanoparticles, we observe a re-increase of the cooperativity, since we observe an hysteresis loop, okay, for these 2 nanometers spin crossover nanoparticles. Of course, the percentage of transition is small because you have only less than 100 centers, ion centers in this case. Okay, so this was predicted by calculation, but we wanted to confirm that. Okay, so we perform Morse-Blower measurements. Using Morse-Blower, it's possible to determine the Debye temperature, which is correlated to the stiffness of the particles. And also, we realize the synchrotron measurements. Okay, Morse-Blower synchrotron measurements. From the dose, it's possible to extract the speed of sound, which also is characteristic of the stiffness of the materials. For both experiments, we have observed that for small nanoparticles, we have an increase of the speed of sound and the Debye temperatures. So these two techniques confirm again that in these small nanoparticles, you have an increase of the rigidity, which can explain the reappearance of the cooperativity in these small nanoparticles. Okay, so now I want to switch on this other family of complexes. So it's the well-known iron triazole family. So here we have iron and its chains, okay, let's say. And we have 3 different triazole ligands bridging 2 iron atoms. Okay. In this complex, the ligand is neutral. This means that we have covalent ion in this kind of complexes. And of course, again, we can change substituent on the triazole ligand, and we can change also the covalent ion, and then you have a big family of complexes, very known family. They are very known because they present also spin crossover at room temperature. So just an example, here you have a heptyl chain, okay, here on the triazole, and the covalent ion is a tosylate. Okay, so you have these complexes. And for these complexes, we have always, we perform two cycles, 2 thermal cycles to check what is the effect when you remove the solvent at high temperature. So the first cycle is with solvent, and the second one is without solvent. So again, for the complex without solvent, we have a spin crossover at room temperature with an hysteresis. This is just to check what is, so it's, here we can see the color change of the samples. This is a team of the normal powder, I mean, because we want to synthesize nanoparticles, but you have to know what we have inside the bulk samples. So if you look at the bulk sample, in fact, you have different size from few tenths of nanometers to micrometric, okay? But you have polydispersity, okay? So this is not convenient if you want to go toward applications. But why you want to try to synthesize homogeneous nanoparticles. Okay, for example, here I will present some results concerning homogeneous media. Homogeneous media means that you have only one phase. So in this case, you just add a polymer, okay, to try again to limit the growth of the materials. Just using this polymer, it's possible to obtain homogeneous particles, okay, but quite large particles. It's not possible, like reverse micelles, to have small size. Okay, you limit the growth, but you have quite large size nanoparticles. Of course, with such kind of size, you have the same property as the bulk, so you have an hysteresis loop centered at 310 K. This is another experiment. In this case, you remove, because if you want to go towards application, and if you use surfactant polymers, this can be a problem, because you have to remove this polymer with surfactants. So we develop also synthesis without polymer and surfactant. Just here you adjust the pH. Okay, so using acid, it was possible to limit the growth of the particles, and we obtain these rods. Okay, so playing with the experimental condition as a strategy, we can obtain different size, but also different shape particles. This is important as a function of, for example, for the electrical measurements, and to try the dielectrophoresis method, it's necessary to have long nanoparticles. This is a very nice result because this new complex, okay, is a new one, present a spin crossover perfectly at room temperature with a large hysteresis. Okay, this is quite scarce in the field, and this is very useful for applications. Okay, so again, if you want to go towards small nanoparticles, the best way is to use reverse micelles. So we again use these techniques to elaborate nanoparticles of this family of complexes. Again, you can play with the concentration, with the ternary systems. And again, we obtain stable microemulsions containing small nanoparticles of this complex. These stable nanoparticles were studied by microscopy, but also by dynamic light scattering, and we can obtain a mean value of 4 nanometers for the nanoparticles. It's important to have this suspension because you can, at the same time, measure the size, but also the spin crossover properties. For example, here you use absorption. Okay, it's a variation of absorbance as a function of temperature. So this way we measure the property of the particles in the solution. So it's not powder, because if you have powder, you can have interaction between nanoparticles. You can have aggregation effect. So using this solution, you are sure that you have suspension of nanoparticles. So you remove the possible aggregation of the particles and the effect of this aggregation on the spin crossover property. Okay, now if you look at the properties, so we just, here is the absorbance at 540 nanometers as a function of temperature. So like this, we can, using this absorbance measurement, obtain the spin crossover properties. So with these 4 nanometer particles, we maintain an absolute transition, but we lose the hysteresis, okay, because it's very small size nanoparticle. So then the idea was to know if it's possible to probe the spin crossover property of one single particles. So for this, we develop, as Azim said, the 2-component systems, which consist to combine the spin crossover nanoparticles with luminophore for the detection. Okay, and again, we need to have an overlap between the emission of the fluorophore and the absorption of the complex in one spin state. Okay, and like this, the absorption change of the complex should, you know that it works now, but at the beginning, this should modulate the fluorescence intensity of the luminophore. This is important for the detection of nano-objects, but also for fluorescent thermometry, and we have seen an example for that. Okay, so just some details concerning the choice of the fluorophore. So we have selected the rhodamine 110 because, of course, we have a good overlap between the emission of the complex of the fluorophore, sorry, in red, and the absorption of the complex in the low spin state. Okay, here you have the high spin state. We have also a very weak thermal extension of the luminescence for this molecule. This is very important, and also a weak photobleaching. This means destruction of the fluorescent properties. Okay, so I pass this. I think you understand. You understood. So here we repeated the synthesis, the reverse Micel synthesis, adding the luminophore in the reaction. Okay, and modifying a little bit the experimental condition. You increase temperature. It was possible to obtain 10 nanometer nanoparticles. Before you obtain 4 nanometer nanoparticles with exactly the same condition, but at room temperature. Okay, so modifying temperature, you increase the size of the particles. And now, if you study the spin crossover properties, the fluorescence measurements. So here we have the emission as a function of temperature. So we can see that we have modulations, and if we report the modulation at fixed wavelengths, we have this thermal variation of the fluorescence, which correspond to the spin crossover phenomenon. So we can probe using this fluorophore. You can probe the spin crossover properties. If you have the good concentration of fluorophore, we can see by the AS the color change of the samples. Okay, so you have demonstrated we have a good modulation of the fluorescence by the spin crossover. The increase of fluorescence is quite important, so we can have a good sensitivity. So this means that you can detect, and we have seen the result, we can detect single object using this kind of strategy. And of the result, you have, remember for the 4 nanometer particles, you have a transition but no hysteresis. And now for the 10 nanometer particles, we have again the hysteresis. So in between 4 nanometers and 10 nanometers, you have really a decrease of the cooperativity. Okay, so now I will just finish with, because up to now, it was just a mixture of the fluorophore and the spin crossover complexes. So it's better to have an engineering of that. So we wanted to develop very nice, good hybrid materials, okay, with combination with noble metals like gold nanoparticles for plasmonic properties, but also for luminescence measurements. Plasmonic is mainly to have a synergy between the gold and the spin crossover complexes. In this case, is more for the detection. So we developed a platform with core shell nanostructures. This is a general pathway of this strategy, but I want to come back to different steps. So here we use the reverse Micel techniques. You use different surfactant. In this case, it's triton Higgs. Okay, it's a different surfactant, and the strategy is to add the precursor for the nanoparticle, spin crossover nanoparticles, but also the precursor, the TEOS, tetrahydroxysilane, for the formation of the silica shell. Okay, so you have all the reactant for the growth of the spin crossover nanoparticles, and the idea was to have at the same time a shell of silica around. Okay, so here we can see the result, the team. So we have about 150 nanometer particles, and if you look at the EDX, here you can see the core of the spin crossover nanoparticles and the shell of silica. It's possible also to map, so you have iron and silica around. So you have core shell structures. In the following step, so you wanted to graft, using the silica shell, different kind of molecules, and in particular fluorophore. In this case, you use the pyrene, which is a well-known fluorophore. This is just a sheaf condensation to obtain these molecules. So you have the pyrene, and you use acetylation to graft these molecules on the surface of the shell of the core shell nanoparticles. You can play also with the concentration of the fluorophore, and we obtain each time more or less the same size of the nanoparticles, about 100 nanometers. Okay, so here you have the photophysics. So the particularity of the pyrene is that you can have monomers and dimers when you have interaction between the aromatic cycles. Okay? So here is reported the emission. So you have a specific emission for the monomer, okay, and a specific emission for the dimers. Okay. So we can see that we have a good overlap between the dimers, the emission of the dimers, and the absorption of the spin crossover complexes again. Okay. And here we report the composite materials as a function of the percentage of fluorophore. Of course, when you have a small quantity of fluorophore, you favorize the formation of monomers, okay, in green here. So here is the emission of the monomer. You have no dimers. And when you increase the quantity of fluorophore, you favorize the formation of dimers. Okay? So for the red, you have mainly dimers, fluorescence of dimers. Okay, so what happened concerning these fluorescence measurements? So this is the fluorescence as a function of temperature. You can see that you have fluorescence intensity variation. When you cycle this composite, the fluorescence decreases a little bit. So you have photobleaching, which is well known for organic molecules. Now, if you look at the fluorescence lifetimes, this is important to try to determine the mechanism involved in these modulations. It's possible if this depends on the distance between the donor and the acceptor, between the spin crossover and the fluorescence part. Okay? If the two components are far, you have normally a reabsorption. You have emission of the photon and reabsorption by the complex. If you have the molecule close to each other, it's possible to have a FRET, resonance transfer mechanism. Okay? So regarding the lifetime measurement as a function of temperature, it's possible to estimate the mechanism. Okay? So in this case, you have a modulation, a variation of the lifetime as a function of spin state. So normally when you have this kind of situation, this means that you have FRET, you have resonance transfer. Okay? But we know that the distance, because we have the spin crossover nanoparticles, we have the shell of silica, and then you have the fluorophore. So the distance between the fluorophore and the spin crossover is quite high. So we think that to explain this fluorescence modulation, it's better explained by the spin crossover induced strain on excimer. So you have during spin crossover, you have volume change, okay, in these materials. And this volume change induces distortion in the dimers. So you modify the interaction between the dimers. That's why you have these modulations. So it's better a spatial distortion on spin and pyrene excited dimer formation and not an energy transfer mechanism, okay, because of the distance between these molecules. This was also demonstrated because we have not the similar effect for the monomers. So this is a good result to confirm this hypothesis. Okay, just to finish, we try also to graph different kind of fluorophore. For here, for example, terbium complexes. Okay, so again, we have good overlap between the two components. We obtain different shaped nanoparticles, modifying a little bit the experimental conditions. Here you have it's more rods, okay, than particles. And again, if you look at the fluorescence measurements, so we can you have an important thermal variation, okay, for this fluorophore. But on the other hand, you have a very nice stability. If you cycle several times the composite, we have the similar response. Okay? The fluorescence is stable, so you have good stability. So you have detection again and stability because of the presence of the terbium. Stability, terbium, the fluorescence of terbium is more stable than organic materials. Now, if you look at again to the lifetime, fluorescence lifetime, you have no effect on the spin crossover state. So this corresponds to a radiative energy transfer. So you have an emission and a reabsorption of the photons. Okay, so we are finished. So I just want to show you where is Toulouse, here in the south of France. So it's a very nice city, well known also for the Airbus company. So I work in Toulouse, but I prefer to show you this city because I live in Carcassonne. Okay? This is a very nice city. Of course, in this city we have two World Heritage sites, which are the fortress and also the Canal du Midi. And so, but using the Canal du Midi, you can go from Toulouse to the Mediterranean Sea, so it's convenient to go to Carcassonne. Okay? And I finished, so I would like just to thank you for your kind attention.
más tímidos. ¿Sí?
Good afternoon. Thanks for the presentation. What is the best size of the nanoparticles for the present spin crossover?
What is it?
Effect. What is the best size of the nanoparticles?
Which one?
Within the reverse microemulsion.
The small one?
Yes. Here.
Here? Yeah.
In the reverse micelles, what is the best size? Or the major size of the nanoparticles?
What do you mean? The size of the
Because
particles
the
is
size-
determined by the size of the micelle.
Okay.
Okay? So you have liquid droplets, water droplets, let's say, okay? And modifying the concentrations and the reactants, you can modify the size of these micelles. And then, as a function of the size of the micelle, we can change the size of the nanoparticles.
Okay.
You can have all sizes.
All sizes.
Yeah.
Oh,
This is very important. Because we need to study the effect of the size. So that we have a technique here which gives you many sizes. It depends on your parameters. Then you can have 2 nanometers, 10 nanometers, 100 nanometers. You can have 7 with the same model specific.
We can have a larger size, but it's not good for the size reduction because we know that more than 100 will have the same property than the bulk.
¿Otra pregunta? ¿Alguien más? ¿Alguien más? ¿Sí? Por favor.
There's an effect on the crystal structure because of the hysteresis. I mean, when the spin crossover occurs, there are different crystallization, or the structure is the same?
It depends on the component. Sometimes you have no structural phase transition, sometimes you have phase transitions. This is depending of the component. In this case, you have no structural phase transition for the class rates. But it's really dependent on the system you use.
Okay. So, if you make crystallization in a spin crossover state and make again crystallization, but in the second spin crossover state, you will have the same structure at the end? I didn't get it.
Yeah, the same question.
Okay.
It depends. As a function of the complexes, it's possible to have structural phase transition. It means in the low spin state and in the high spin state, we'll have different structural phase. Okay? But sometimes you have the same structural phase.
Okay,
You have just an increase of the volume, okay? But you keep the same structural phase.
Okay.
But you have the two possibilities. It's really dependent of the material.
Okay, thank you.
Una última pregunta. por acá. ¿Alguien más? ¿Alguien más para preguntar? Bueno, comentarles que el profesor Acedín y el profesor Lionel Salmón van a estar aquí hasta el miércoles para que, si quieren platicar con ellos, preguntarles posibilidades de hacer estancias o incluso el doctorado en Toulouse, hay buenas oportunidades para hacerlo, entonces podrían platicar un poquito más en corto con ellos. Entonces, bueno, me gustaría pues agradecerles al profesor Acedín Boussexou y al doctor Lionel Salmón por haber dado estas interesantes pláticas y bueno, pues para el instituto es todo un honor el que hayan estado el día de hoy en este coloquio especial. Merci beaucoup.
Y bueno, agradecer. Una pregunta. Sí. Sí, justo comentarles que en el posgrado en Ciencias Químicas, justamente en el programa de maestría y doctorado, acaba de ser aprobada la posibilidad de que en el doctorado puedan realizar el estudio en cotutela, es decir, que puedan obtener el grado tanto en México como en Francia. Así es que bueno, este es un gran avance dentro de este proyecto de colaboración del Laboratorio Internacional Asociado, que ya tiene varios años que se ha iniciado. Y bueno, primero se habían hecho únicamente el doctorado allá, tenemos 2 estudiantes que hemos mandado allá. Bueno, la primera fue Edna y está Dolores también haciendo el doctorado allá. Sin embargo, a partir de este año es posible hacerlo en el programa de Ciencias Químicas en la modalidad de cotutelas, lo cual pues bueno, puede abrir más el panorama de fortalecimiento de esta colaboración entre los grupos que tenemos en México y los grupos que están en el Laboratorio de Química de Coordinación. Entonces, pues bueno, agradecerles a todos y bueno, agradecer de nuevo al profesor Albert Fert, merci beaucoup, por haber venido a esta plática. Bueno, gracias a todos que vinieron también. Bueno, justamente el doctor Norberto Farfán es el líder mexicano de este Laboratorio Internacional Asociado y bueno, pues justamente agradecerle que hayan estado aquí, igual que a los colegas que nos hicieron favor de venir a esta interesante plática, a estas 2 interesantes pláticas que estuvieron aquí el día de hoy con nosotros. Muchas gracias. En nombre de nuestro director, el doctor Miguel Alcubierre, pues agradecerles de nuevo su presencia en este coloquio especial de investigación de nuestro instituto. Gracias a todos. Buena tarde.